Welcome everyone to truth tables, if I can say the word. The truth tables are easier than it is for me to pronounce those words, apparently. So before we introduce what truth tables are, I want to give some context, which is a little exciting. I really like these next few videos because they really put and connect a lot of things together. So one of the topics that we've talked about in this class is the difference between an intension and an extension. And we talked about this, we introduced this really when we started talking about sets, right? An intentional way of defining set could be saying like, the set of all even numbers. Whereas the extension, remember, so intension is like describing something, and extension is really listing it all out, like really being explicit about what we're talking about. So the extension here, right, would be 0 to 4, etc. And it also goes in the other direction, right? Etc. like that. So these are the same sets, just one's the intentional definition, one's the extensional definition. Well, we also did that a little bit when we looked at relations. And this is going to come into play as well when we get into predicate logic, because this is exciting, but predicate logic does have to do with relations and functions. Just good old chapter 3. So if I have an intentional relation, really, some of these words sound very strangely, right? This was for sets, but remember this also works for relations. We can have some kind of intentional relation, which could maybe be like is daughter of, for a relation where X is related to Y if X is the daughter of Y, okay? And again, the author of this textbook likes The Simpsons. So for example, that relation would be the set. Remember, all relations are just sets of ordered pairs. So it could be the ordered pair Lisa and Homer, because Lisa is the daughter of Homer. This is the extension, right? And then so on and so forth, right? We'd also have the ordered pair Lisa Marge. I don't know if I've ever seen an episode of The Simpsons, but I know who these characters are, I think. And so on and so forth with all the, daughter, parent combinations of Simpsons characters. Okay? Well, now we're in chapter 8. Now we're talking about propositional logic. And we're going to have something similar for, how do I want to write this? For logical operators. We've kind of talked about the intention so far. So for example, we say that both propositions must be true. What logical operator is that talking about? It's the AND operator, okay? Now, one of the ways that we can talk that, again, this is the AND operator. We're going to get into the extension of this. And where am I going? The extension of that is a truth table. Okay? So that's what it's going to look like. We're going to have a table of all the possible values of X and Y, and then the value of X and Y. So 0, 1. Sorry, let's go in order. 0, 0, 0, 1, 1, 0, and 1, 1. And also when we're doing these truth tables, we are going to be doing these where 0 signifies false and 1 signifies true. Okay, very common shorthand. Also, should be familiar. It's essentially Boolean logic, right? Okay, so if these are both false, is the AND statement true or false? No, it's false. If only one's true, the AND statement's still false. It's only true, right, if they're both true. So this is the extension, the extensional way of viewing this logical operator. It's a truth table. Truth tables are just the extension for these logical operators, which is pretty cool. We just list it all out. So with that being in mind, I got 2 exercises for you. You can do them or not do them as you prefer. I want you to create a truth table for all our operators. Okay, so your table is going to have all the values of X's and Y. And then you're going to say, okay, what are the value of X and Y? X or Y, X XOR Y. That's kind of weird to say. X implies Y, and X equiv Y. So you should be able to fill this in. I highly recommend you pause the video, fill this in. And then after you're done with that, I want you to do another one. I want you to see, this one's a little tedious. So again, if you want practice, if you feel like you need practice, definitely do it. If you feel like you're good on this and don't need the practice, feel free to skip it. C XOR A and not B implies not A. This one, we're really going to show how it's useful to do a truth table in steps. So this one's a little trickier. I do actually recommend you kind of see how I do this. So pause the video if you haven't already and fill in this truth table. So, here are all the possibles values, all the possible combinations of X or Y. We are enumerating all the possibilities for X and Y. There's 2 choices for X, there's 2 choices of Y. So by the fundamental theorem of counting, right, there's 4 choices total, which is kind of fun. So again, we already did this first one. On the last page, X or Y is when, at least one of them is true. Could be both. So the only time that's false, right, is when they're both false. X XOR or Y, right, is going to be true when either one but not both is true. So it's only going to be true here. It's almost the same as the previous one, right? We just can't have both. X implies Y. Remember, this was the tricky one. The only time this is false is if the premise is satisfied and the conclusion is not. So this is the only time this is false. Everywhere else it's true. And then remember, this just means they're the same. So they're the same right here, and they're different here. And again, I mentioned it earlier, oops, right? But these 2 things are kind of like, they're always opposites from each other. If one is true, the other is false, which we'll get into in the next video. We could create a tautology if we used these a little bit. Anyway, if we did not one of these, equiv with the other one, but that's a little bit in the future. So that's what all of our logical operators look like in a truth table. Well, almost all of our, I guess I skipped one, huh? Not X, what does that look like? Well, if X is 0, this is 1. If X is 1, this is 0. It doesn't really matter what Y is for not X. Now we have our 6 logical operators here. So if you want to use a truth table for something messier, what you're really going to want to do is break it down into steps. So we need A, B, and C. How many rows do we need here? A can be 2 things, B can be 2 things, C can be 2 things. So by the fundamental theorem of counting, we are going to need 4 rows. How can we find every single permutation of these values? Well, we had a couple of algorithms for finding every kind of permutation for values of A, B, and C. We could do 4 zeros here and then 4 ones here. That was a common one. And then we just go 0, 0, 0, 1, 1, 0, 1, 1. And then we just do the same thing again. Ah, look how it's all going to play. Fun fact for anyone who's hasn't seen this, notice that when you're looking for all permutations here, it's just like counting in binary. Right? That first number is 0 in binary. The second number is 1 in binary, 2 in binary, 3 in binary, 4 in binary. So one of the things that you can do to go through every single combination of zeros and ones is actually just count and then convert that number to a binary string. All right. Which, funnily enough, I was actually having a conversation with a student about that pretty recently. So, and now we just approach this truth table in steps. We always start on the inside and work our way out. So we have parentheses. We're going to need to know this. So let's start by making, what is not B? Well, that's easy. Not B is just the opposite of whatever B is. Now, what does A and not B look like? Well, now we look at these two and do the AND operation between just those two things. So it's only going to be true when they're both true. And I believe this is when they're both true. It's got to be down here because these are the only ones where A is true. And yeah, here's when not B is true. Oops, I lost that. So now we take this and we want to XOR that with C. So now we're going to look at these two and look at exclusive OR between those two. All right, so it's going to be C XOR that. And it's perfectly fine to use shorthand like this if you want. The author does some really cool shorthand that I'll introduce in the next video. But yeah, it's either going to be C XOR this. So when exactly one of these is true, not both. So that should be the only times where exactly one of those two things is true. Again, we're looking at these two columns. When is only one of these columns true? And I believe we've got it all written down here. So I'll fill in the other ones with zeros. And finally, now we just take this part. Again, all right, we will use another notation here. We could call this whatever we want. We could call this a blue heart. So when is a blue heart imply not A? Oh, we should actually, all right, let's be very precise. Let's do not A as well. We're going to need that. What is not A? 1, 1, 1, 1, 0, 0, 0, 0. Now, finally, we're curious, when is heart imply not A? And it's totally fine to do this. This is kind of like essentially what variables are all about. Variables don't just have to be letters. Variables can be any kind of picture you want. The important thing is to say, hey, I'm going to refer to this as some special name, some special picture. So this is totally legitimate to write it this way. All right. So remember how implications work. The only time an implication is false is if you have the premise and you don't have the conclusion. So the premise is heart. So we're looking at all the times where we have the premise satisfied. Oh, so if the premise is satisfied and the conclusion's not, it's false. Otherwise, we're true. So I'm just going to look at all the points where the premise is satisfied and the conclusion's not. So premise is satisfied, but so is the conclusion. Premise is satisfied. Okay, here, premise is satisfied, conclusion's not satisfied. So this is going to be false. Premise satisfied, conclusion not satisfied. This is false. That's the only time implications are false. When the premise is satisfied and the conclusion is not. Everywhere else is true. So what we've done with this truth table, and yes, it was a little tedious, and yes, it took a lot of time, is we really just found out every possibility, depending on what A, B, and C are, for this really, really messy thing. And of course, this is very silly, right? This has no meaning to us. This has no point. This has no purpose. This really is just an exercise to get practice doing messy things. But in reality, a lot of times, if you're maybe if you're designing a program or you're designing some kind of logical thing, right? You might want to know, like, okay, well, I have all of these conditions. How often are these conditions going to be true, right? What are the actual situations where they're true? Well, we might run into some tautologies, which we'll talk about in the next video, where it's always true. And if something's always true, why do we have an if-then statement in the first place? Okay, that's just bloat. All right, so that's really what we're doing here. This is almost a tautology, right? This is almost always true. There's only 2 times when this is not true. Because remember, what is this up here? This is a compound proposition. This is just a proposition that is either true or false. And we found out it's, most combinations make this true. There's only a couple things where it's going to be false. All right, that's pretty much it for this video. Did get into kind of a long a lot of examples, but hopefully it gives good practice for these logical operators and a way of organizing them with truth tables. Take it easy and let me know if you have any questions. See ya.